Hello.
Hello.
Do you see the screen now?
Yeah.
Yes.
Okay. So we will start now with a new chapter, which is vectors and forces. So first, we will see how to add forces. Okay. We have seen in the previous chapter the geometrical methods to add forces. Now we will introduce the analytical method. Okay. So here, if I have any force, I can decompose it into a frame into components. Okay. So for example, here force F is divided into X and Y components. So if I have to do addition of forces, if I want to use the analytical method, all I have to do is to find for all forces the components along X and the components along Y, and then the resultant force will be obtained by adding the X component together and adding the Y components together. So now, when I want to do addition of forces, okay, I have two representation methods: the scalar notation and the Cartesian vector notation. When we talk about scalar notation, this means that the magnitudes and sense of the components are expressed by algebraic scalars. Okay, so for example, in this case, I just represent any vector by components. So you know, for example, I put like this. Let's say vector f1. So vector f1 is equal, I can give it like this, -3 and 2. Okay, this automatically will mean that we have that the x component is negative, so I have a projection on x -3 and a projection on y equal to +2. Okay, and of course the negative or positive sign depend on the orientation of the components relative to xy. So when I put f1, so here I have f1x equals to -3. Okay, so this means that the projection of f along x-axis is in the negative direction. Okay, while for the Cartesian vector notation, I always express my force as an addition of two vectors. Okay, so instead of writing it like this, if I want to do the Cartesian notation, I will write like this: f1, of course, vector. So I put an arrow above it. F1 vector is equal to -3i plus 2j. Okay, and in this case, if you want, we say that the components will be positive numbers, but what will indicate the direction is the sign of the vector, of the unit vector. So if it can be, it is equivalent to writing this: it's 3 times -i, okay, plus 2j. Okay, this is why we say that in Cartesian vector notation, the vectors I and j are used to specify the directions. So when it is in the negative direction, I put minus before the vector. So in this case, the components of the forces are always positive numbers, but the negative sign is given to the vector. So it's just a way of notation. Okay, and both cases will give me at the end the same result. Okay. Now,
Doctor,
yes,
can you please repeat the scalar a little bit?
yes, of course. So the scalar notation, instead of putting, if you want, the vector as a summation of two vectors in I and j, and for example, if I have, I will draw a figure. If you have, this is the y, this is x, and you have a vector like this, okay? You can define it, you can write it in two ways. You can write, if this projection here, for example, This is the projection on X. This distance is equal, let's say, to 5, for example, or 5. And the projection on X, this distance, if I project on Y, this distance here is 4. Okay. If you want to use the scalar notation, then you can say that vector f like this. If it has two components. Along x, it has a positive component, so it's plus 5. And along y, it has a negative component, so it's minus 4. This is the scalar notation. Okay. Now, if you want to represent the vector as a vector using the Cartesian vector notation, you will write that f as a vector is equal to 5 vector I, okay, plus 4 times minus j. Okay, so in this case, in the vector notation, these components are always positive, but what will give me the sense if it's positive or negative is the vector. So if it is along minus g vector, so it's opposing to g. Okay, and here because it's oriented along positive x, so it's plus I. Okay. On the other hand, for the scalar notation, I don't put the sign is directly given to the component, while in the vector notation, the sign is given to the vector. That's it. Okay.
Thank you, Doctor.
Any other question on this? Okay, so let us continue. So now, if I want to add vectors, okay, what I will do, I will resolve each force in x and y components. Then I will add components using the scalar method, or also the second method is to the geometrical way. I can get the resultant by addition of the resultants of x and y components using the parallelogram law or triangle law. Okay, but once I have done the big work to find all components of forces, then of course it's easier to use the analytical method. Okay, because once I have the components, I can find easily the resultant force and the angle, and you will see how. So, for example, here I have three forces. I have F1, F2, and F3, and I want to add them. Okay, so what I did, I decomposed each force into components. So as you can see here, F1 can be decomposed into X and Y component. The same for F3. Of course, to do the decomposition, they should give me information. They should give me the angle. They should give me the magnitude. Okay, and for F2, also I divided into two parts. And now I will have three components along X, three components along Y. And I can see that F1 and F3 has positive X component, while F2 has a negative X component. And for Y components, F1 and F2 have positive Y, and F3 has a negative Y component. Okay? Once I determine all components, now I can say that if I want to calculate the resultant force, I can write that the resultant force X component will be equal to F1X plus F2X plus F3X. Okay, and as we said here, I am using the scalar method, so the sign will be, they can be positive or negative. Okay, so here, for example, in x direction, F2x is negative, while F1x and F3x are positive. And to calculate the resultant in y, I say that F resultant in y is equal to F1y plus F2y plus F3y. Okay, now if I look at my figure here, how to find the total resultant? So whenever you find FRX and FRY, okay, We know that since it is a rectangular frame, so the angle here is 90. Okay, so this is a 90 degrees angle. So since it's a 90 degrees angle, then we have that the resultant force can be calculated by what? From Pythagoras theorem. Okay, so I can say that Fr is the radical of Frx square plus Fry square. And how to calculate the angle here? How to find angle theta? What can I write?
Tangent minus 1.
Yes, exactly. It's tangent minus 1 of this edge, which is Fry over Frx. Okay? So if we see it in the next slide, we have two possibilities for the addition. Okay, we can write it in scalar form as I did with you, or we can do the Cartesian notation. We can use the Cartesian notation. If we use the Cartesian notation, then as you can see, f1 has positive components along I at j, so it's plus I plus j. Now along for f2 it's minus I and plus j, so it's minus f2xi plus f2yj, and for f3 it's positive I negative j, so plus f3xi minus f3yj. And now when we do the addition, we of the two vectors, the total component in I will be f1x minus f2x plus f3x. So the difference between what we did and what they did is that they considered that all values are positive and the sign is given to the vector, while in the scalar notation, f2x will be itself negative. Okay? And in J, the total value will be f1y plus f2y minus f3y. While if you use the scalar notation, it will be f1y plus f2y plus f3y, but f3y it will be negative. Okay? So now, after finding the resultant in this form, to calculate the the resultant force, I add the x components together, I add the y components together, and then I say that to calculate the magnitude, it's radical of f square rx plus f square ry, and to calculate the angle theta, it's tangent minus 1 of fry over fr. Okay, so this is the analytical method to find the resultant force. Any question on this? Okay, just one remark before we stop. If you have, for example, the force like this, okay, and you want to calculate the angle, or like this, for example, okay, then to calculate angle theta, what you do is you can define theta as this angle, this one, okay, and then you are in the fourth quadrant. So to calculate theta, you do tangent minus 1 of the absolute value. Because in this case, if you are here, for example, you will have fry negative. Okay? So always to find the direction, specify the quadrant where you are, put on the figure the angle you want to find, and then take the tangent minus 1 of the absolute value of the ratio. Okay? So we are done for today. We will continue next time. Any question before we close?
Yeah, doctor, the session will be posted to Blackboard.
Yes, of course it will be.
Okay, perfect.
Doctor,
Yeah.
excuse me.
Yeah.
In any quadrant, we put
Yeah.
absolute value of
Yes.
fy
Yes,
over fx.
in any quadrant, yes. If you are
Yes,
here,
and
for example, look, if you are here, this is theta for you. Okay? If you are here, this is theta for you. Okay? So this is why I will put absolute value, because if you have a negative tangent, then the angle will be higher than pi over 2, it will give you the angle with the positive axis. Okay. But even look, and even if you get from the calculator an angle higher than 90, but you still have two possibilities. It can be, the direction can be up or down. Okay, because you know that the tangent of an angle, it will give you the angle plus k pi. Okay, so if you want to have the accurate angle, you need to know in which quadrant you are. So to simplify, the first step, determine your quadrant, and then find the angle with the axis that will give you an angle smaller than 90. So if you are here, you calculate the angle here. Okay, if you are down, you calculate this angle. This is the idea. This is why I put that on my figure, and then I take tangent of -1 of the absolute value.
Thank you, doctor. And concerning the introduction, we study it as any other chapter, or it's just an introduction? No, we do practice for the.
The introduction, if you want, yes, it's you need to know it because it will help you to continue, and it includes the geometrical analysis. We will use it a lot. So yes, of course, you should study, and we will practice on it in review problems of chapter 2. You will have geometrical methods.
Thank you
So
so
it's
much.
like a part of this chapter actually. Okay.
Yes, yes.
Thank you.
Welcome. So see you next time. Bye bye.
Bye bye.